4-phase power, cold start. There's the temperature. There's the standing millivolts, 200 millivolts, and the genset. A slow rotation. You see the wave. The standing ohms of the generator is 4 ohms. Watch when we turn it. The generator is wound at 29 ohms. So we've changed the magnetic ordering and lowered the ohms resistance in the wire. You see how it now goes negative? It's pegging the needle negative because we're passing 0 ohms and going the other direction. We'll talk about superconductivity and the misnomer of checking ohms through a superconductivity wire next. We're at 0 hertz through the drive. Millivolts, hertz, drive, input amperage, output amperage, heat soaks. No load, cold start. We're just going to pay attention to the oscilloscope. We're coming to 10 hertz. Hertz, 21 volts, frequency 19, perfect power. Let's check that. 50%, perfect power. Check the volts, DC. Okay, we're loading. Check the hertz, DC. Perfect. We're loading. Let's check the power. Almost there. 48, because we're loading. The genset's cold, but the wave is stable. Okay, now we're just going to stay on AC percentage for a moment until we get to the next threshold. And we're just going to watch the oscilloscope and the hertz of the drive. You can already see the rotational of the tunneling effect of the Cooper-Puchta chains in linear magnetism 4-phase plasma power. Okay. Now, there's the heterodyne. You can clearly see at just 12 hertz, 12.6, the heterodyne. And it popped into another phase. Now, you can clearly see on the camera the 2 hots and the 2 resonating legs that are self-regulating the power so that you don't overload the circuit. On the oscilloscope, we see the lines all one color, but the camera effect allows us to, you, the audience, to see a truer story. The 2 would be AC. The light ones would be the regulating. Okay. Now we're going to step it up a little bit more. Okay, now we're at 3-phase power. Imposed 6 regulating and 2 ground states. Now you can clearly see the bow tie of superconductivity. Still perfect power. Perfect power. We're just at 25 hertz. Our load is 2 amps. And our draw is 2.1 amps. Perfect power. We have no losses, a 0.001% of loss. Mostly because the inefficiency of these windings, but they're all the same. They started at 14.9 ohms. Now, after being conditioned, they're 14.2 ohms. So we've imposed the energy and changed the magnetic ordering in these heating elements. We're at 53 volts now. 47 hertz. Perfect power. AC. Now let's go to DC. Now the DC volts are gone. Okay? And you notice it's not going from positive to negative. It's heterodyning the current. Okay? Saturation is bouncing back off the genset in a perfect heterodyne magneto-resonance. The saturation current is self-regulating between the coils and the genset. So there's no heat between the two, only where it needs to go. The genset is not going to get hot. This generator had been sitting on the bench in the specs of the empirical data at 1,000 watts. The coils would go over saturation, over 180 degrees, and run away, and the thing failed. This will never get over 140 degrees, 150 degrees max. It doesn't matter the load, anything. You could dead short it, and it would never get over that. Way under the threshold. We're going to prove that today. Okay, now we're going to go to hertz again. Still perfect power. There's no negotiable DC volts because we are technically in plasma. Now, we're going to watch the oscilloscope again. Perfect heterodyne resonance. Okay? Perfect resonance. Let's check. We are at 31 hertz. The drive with this pulley was perfectly timed, so this generator produced 60 hertz at 60 volts at 294 RPM. This new pulley doubles that, so we can bring the speed up. Before, in the other videos, we were at 60 hertz drive under load, producing 64 volts and more amps. Now watch. Let's go to AC, or let's go to DC frequency. Perfect, 60 hertz DC. Okay? Now let's go to AC. 60 volts AC, perfectly timed with the DC plasma. 4 squared over Faraday. There's your 60 hertz AC. There's your percentage. Pretty damn close to fit the perfect power because we're still loading. These coils are getting warm. Okay? So we are definitely pushing the motive force of plasma to do work in a very safe manner. Here's the light bulb. Running cool. Okay? That light bulb should have taken the least path of resistance, and that light bulb should be cherry red hot right now. That's not going to ever happen with linear magnetism and four-phase superconductive power over our grid. I'm just going up the hertz a little bit, and we're back in to the bow tie of superconductivity. Now we're back in a perfect magneto-heterodyne resonance in the bow tie of superconductivity. You notice the charges going from one side to the next because it's self-regulating. So now let's look at our AC. Now we're coming closer to 50. Let's look at our hertz. Now we're 81 hertz. Or 81 volts. Now we're 72 hertz. This is a polyphase generator that can't make over 60 hertz. But we're at 72. Look at our ohms. Can't even get off the needle. It would like to, but it can't. Because the power is in a perfect Cooper-Puchta superconductive tunnel. There's our temperature. We didn't even made it over room temperature on the coils. There's our load. 3.4 amps. There's our draw, 3.3, almost perfect power, no losses. Now, there's your three-phase power again, but we did not touch the oscilloscope is because the potential is naturally spraying the plasma on the oscilloscope, and there's obviously more potential coming through the line. So let's prove that. Now we're at 80 hertz, but we're only at 42 hertz on the drive. We've doubled, okay? We've doubled the efficiency. Now, technically, by law of Ohm's law and Gibbs and Tesla, over Maxwell, over Heaviside, over Faraday, we are definitely double over unity right now. Let's see if we're still making heat. 300, 350. 300, 350. Even three-phase power, but look at our light bulb. 200 degrees, running cold. Okay? Now, let's push it a little further. We're at 42 hertz on the drive. We're back in the bow tie of superconductivity. Does that look familiar? It looks just like my linear magneto wave. Copyrighted circuits by David Puchta and the applied patent to superconductivity over our grid. Now we are way over Faraday, pushing superconductivity and magnetism at its bay. respectively, ladies and gentlemen, bus driving Michael Faraday and backing up over Nikola Tesla. Let's push it a little further. We're back in the bow tie of superconductivity. Now we are max on the drive. Our RPMs are well, look at the other videos. We're at 500. We're doubled the RPMs. We're at 599. Okay, here we go. All right, 573. We're going to call it 570. Close enough. There's our amp load. and a half, just under 6.5 amps. 5.3. So let's just take this and jump over here and see how close we are. 6.8. Okay. .3, and we're making heat. Now we're at 500 degrees. You see how quick the heating elements heated up? But look at our light bulb. Still technically running cold. That's a 350 to 400 temperature light bulb under regular electricity. But look at our Hertz. Gibbs' law tells us now we're 4 square over unity. Let's check the volt, DC. Nothing there. Let's check the Hertz, DC. 113 Hertz, perfectly tied to the volt. Let's check our percentage. Perfect power, 49.7. A third of a percent of a loss. That's pretty good. That's 1% per leg. That's 0.1% per leg. Power companies would love this phase angle under load anywhere you go. Now let's go to volts. 128 volts. Look at our frequency. What's our percentage? Pretty damn close to perfect power. At 60 Hertz drive, we're 4 times over unity. Mathematically proven. Now let's slow it down and watch what you'll see. We're just gonna slow all the way down and look at one specific parameter. An oscilloscope needs an electric charge to put the plasma on the screen. Otherwise, you get a dot. Ladies and gentlemen, I would like to let you know, under non-disclosure clauses, we have Sempra Energy viewing this demonstration. Thank you and have a nice day on superconductive for phase power over our electrical grid.